Hi, today we're going to be talking about the relativistic addition of velocities. And so to begin, we'll talk about our classical understanding of what that is to help us understand it when it becomes more complicated. When I say classical, it just references the addition of velocities at relatively lower velocities compared to ones closer to the speed of light. And so our basic understanding of this is that v is equal to the speed of an object relative to the Earth, and our u prime is the speed of a different object relative to the speed of the first. And our u is going to be the velocity of this object relative to an earthbound observer. So to do a problem to illustrate this, we're going to imagine we have a child on a sled right here getting pulled by his dad, with an observer watching from this spot in front of them. So we'll imagine that this dad is pulling the sled at a speed of 1.5 meters per second. And let's say this kid throws a snowball in this direction at 1 meters per second. So the question is what speed does this snowball approach our observer? So v will be our 1.5 meters per second, and the snowball relative to the sled is going 1 meters per second. And that'll be our u prime. So relative to this observer, this snowball is approaching the observer from his perspective at 2.5 meters per second. And it's important to recognize what direction the objects are going in. Because say if we have the same dad pulling the sled with his kid on it, and the kid were to throw the snowball backwards at 1 meters per second, while the dad was still going forward at 1.5 meters per second with the sled, then we would calculate it like this with the observer right here. So it would be 1.5 meters per second. And now because this is going away from our observer, we'll make this negative, which would give us ultimately an answer of 0.5 meters per second. And that would be the what this snowball would appear to this observer right here would be 0.5 meters per second. And so classically, this is how we've understood how velocities add. But when we get to higher speeds, you'll see why this no longer works. So let's work in another problem to illustrate this. So according to our classical understanding, u will be equal to our u prime plus our v. So let's say we have a car with headlights. Okay, and then our observer will be right here, off to the side. And so let's say there's headlights are turned on and the light is shining forward. And we know that the speed of light is c, where c is equal to or about 3 times 10 to the 8th meters per second. And let's say this car is going 10 meters per second. So if we go with our classical understanding of how velocities add, then this would be speed of light plus 10 meters per second and equals something greater than the speed of light. which we know is not possible. You can't go faster. This will not be going faster than the speed of light, according to this observer. So how do we correctly calculate this? Well, the correct way to calculate relativistic addition of velocities is this equation. So we have our same equation is on top. That hasn't changed, but we're divided by this new part. And this really is the same equation we've been using up here, but at low velocities, say like our 1 and 1.5, that would give us another just 1.5 divided by the speed of light squared, which would give us a very, very small number, which would ultimately be like just dividing by 1. So that's why this appeared to be correct in the past for these slower velocities. But once we get to up to the speed of light and these greater velocities, you'll see how it correctly works without going over and breaking our understanding of the speed of light. So to illustrate this, we got some more problems. We'll have 3 different rocket ships flying through space, and each one will be heading towards Earth. Okay, so the first rocket is going to have, let's say, a laser pointer. And this laser pointer is going to shine at Earth, going at the speed of light, while this rocket is traveling also towards Earth at half of the speed of light. So we want to figure out what is the velocity that this light is traveling towards Earth. So if we calculate this using our new equation, I'll write it out for us again. That would be c plus 0.5c over 1 times 0.5c times c over c squared equals u. So in this problem, the simple addition on top will equal us to 1.5c. All of these c's will cancel because there are 2 c's on top and the times divided by c squared. So that'll give us 1.5 on the bottom. And as you can see, these will cancel. So u will equal just the speed of light, which will correctly match our understanding that nothing can go faster than the speed of light. And that would make sense that this laser would approach at a constant speed and not be affected by the speed of the spaceship. Okay, so what happens when we're dealing with the rocket ship? There are 2 different rocket ships and they have canisters that they will eject. One will go away and one will go towards Earth. So the first one, we'll say it approaches towards Earth at 7.75 times the speed of light. And this other one will go away at 0.75 times the speed of light. While our rockets both approach at half the speed of light. So let's do the math to see how this equation would work and give us the correct understanding. Because if we were to add these together, it would give us 1.25 times the speed of light, which again we know is incorrect because we can't go faster than the speed of light. So we calculate it over here like this. 0.75 times the speed of light plus 0.5 times the speed of light, and the bottom 0.75 times 0.5 divided by c squared is equal to u. So again, we know that our c's will cancel, and so we're left with a simple addition at this point. So we'll have 1.25 times c on the top, and on the bottom 0.75 times 0.5 will equal 0.375. So we'll be given this. And so again, it's just simple. I'll write it again so you can see clear. Simple addition or division. And so looking at this fraction, we know that this is going to be less than 1. So this would give us a correct understanding that this, while it is going faster due to the velocity of our rocket ship as well, it is still less than the speed of light. And then looking again at this next problem with the canisters going away, it again relates similarly to when our snowball was being thrown away. Will come at Earth at a lesser speed than this, but it's not just simple subtraction. If it was like before, we would get an answer of negative 0.25 times the speed of light, which again, we will see that this is not the correct answer. So writing it out, it's going to be negative 0.75 because it is going away from our Earth. And then adding the next part of the velocity of the rocket ship. Right in, just a problem here, c squared. So again, these c's cancel out, so we have a simple addition on top and bottom. So the top will turn out to be 0.25, negative 0.25 times the speed of light. And on bottom, we are, this is the negative, left with 1 plus negative 0.375 is equal to u. So when it's minus 0.375, I could do the math. You can do the math yourself, but ultimately this is going to be a different number than our 0.25c. It won't equal that. It'll be different because at these, when we're close to the speed of light, it does not work like in a simple addition like we learned before. It works much differently. So pause if you have any questions, or feel free to rewind. Thanks for watching.